next table that we get is the MANOVA F values. So after boxes M test, which is not a great test of the quality of covariance matrix, we actually get the ANOVA. You can ignore the intercept section. I think it's not very informative in most cases, and just go to the second row, and this is where my independent variable is, education level. Okay, and SPSS gives 4 different approaches to calculating an F value for MANOVA, and you've got to choose one. Roy's largest root is the most powerful, but it's also the most susceptible to deviations in your covariance matrices. Roy's largest root has been criticized so much that some people say you shouldn't use it under any circumstance. And I'd be inclined to probably endorse that approach as well. If you had a perfectly normal distributions and perfect covariance matrices that were exactly the same across all groups, then maybe you would interpret it, but in most cases you're not going to get it. The vast majority of people report either Pillai's trace or Wilks lambda. Pillai's trace is the least sensitive to violations of the assumption of covariance matrix. So if you have a hunch that you have violated the assumption and you want to keep yourself protected from rejecting the null hypothesis when it's in fact true, then you should use Pillai's trace. And in this case, Pillai's trace, the value is 0.30, but the actual F value is 11.94, and it's significant at p less than 0.001. So we've rejected the null hypothesis that the education levels are the same levels of intelligence based on a MANOVA-derived combined dependent variable by combining the 9 dependent variables together in a canonical variate. And I'll explain that a little bit more later. Partial eta squared is equal to 0.15. So about 15% of the variability in intelligence across all 9 dependent variables in a canonical MANOVA-derived estimate is being accounted for by the 3 group levels. This is basically eta squared in the ANOVA case, but it can be interpreted in the same context as the ANOVA case, but it's actually MANOVA. Wilks lambda is a little bit larger, so you'll have a choice to choose one or the other. Pillai's trace is usually the smallest, but it's also the most robust to violations of assumptions of covariance. So you have the option of using Wilks lambda, so either 11.9 or 13, and significance level, both p less than 0.05, and then you get slightly different partial eta squared values. So once you reject the null hypothesis with the MANOVA F, so either you're using Pillai's trace or Wilks lambda, you then would follow it up using the first approach to doing MANOVA with a series of one-way ANOVAs. So I've rejected the null hypothesis based on a combined variable, combining all dependent variables. Now I want to look at the individual dependent variables separately with ANOVAs. And before I do that, I have to accept the homogeneity of variance assumption, and in this case it's being tested with Levene's test, and across all 9 variables, dependent variables, the homogeneity assumption is being satisfied. None of the p, except for 2, the p-values aren't less than 0.05, and ANOVAs are relatively robust to violations of homogeneity anyway. So unless the standard deviations that I looked at up here were something like 3 or 4 times larger than each other, and the sample sizes weren't equal, then I would be concerned. But given that the sample sizes are roughly equal and the standard deviations are all within about 20% of each other, I'd be satisfied that even though I've rejected the null hypothesis in these 2 cases for memory 3 and spatial 1, I'd still feel like I could go on and do the ANOVAs.